Hello everyone, let's take a look at our next problem. How many ordered pairs xy of integers is it true that 0 is less than x is less than y is less than 10 to the 6, and that the arithmetic mean of x and y is exactly 2 more than the geometric mean of x and y? Okay. Well, there are the formulas for the arithmetic and geometric mean are pretty straightforward. So, I think once we write down those formulas and write down exactly what's said here, I feel like this is going to turn into a geometrical problem where we're counting points inside of an ellipse or something like that. So let me write down. Okay, let me just write down, summarize what's going on in the question here. So we want the arithmetic mean is exactly 2 more than the geometric mean. So the geometric mean is equal to this, and we have to add 2 to the geometric mean to make these equal. So what I'm thinking of doing now is, let's get rid of that fraction. And now rearrange this and square it to get rid of the root. So I'm not sure exactly where we might go with this. There's a lot of sort of common factor looking things here. So even if we just start playing around and taking some guesses, we have strict inequality between these numbers. They're strictly positive. X is strictly less than y. So, the first possible candidate is x equals 1 and y equals 2. And if we substitute this in here, what are we going to get? 1 minus 8 times 3 plus 16, which is certainly not equal to 0. So in fact, here another thing we note here, this is a multiple, this is a multiple of 16. This is a multiple of 8. So this number, x minus y, is going to have to be a multiple of 2, right? X and y are both even or both odd. Because if x and y have different parity, then this whole thing will be odd. So, I know then that x is going to be equal to, or I should say, y is larger. So y is going to be equal to x plus 2k for some value of k. And in fact, we might even be able to say 4k. That's divisible by, this is divisible by 4. That's divisible by 4. I think we might be able to say 4k. I'm going to come back to that in a second. I'm going to continue with this relation that y is equal to x plus 2k and see what happens. See if we can find all values of k that work for this. And then see if I can argue that maybe we could use 4k here. Okay. Okay, so what I have now is a quadratic equation for k. In fact, let me simplify it a bit. Let's make it look like a quadratic equation for k. Okay, so what I'd like to do is I'd like to solve for k. We need k to be an integer, positive. So when we write down the solutions or the roots of this polynomial, we'll just have to find values of x that make it possible that k is a non-negative integer. Actually, we can simplify the polynomial first, right? We can divide it by 4. Okay, so we need, well, this thing underneath the square root sign can also be further simplified. Okay, and we know that x is greater than or equal to 1. So in fact, we're not going to take the negative square root sign. We need the positive square root sign. Okay, so this is interesting because it says that if we fix x as any value between 1 and a little bit less than 1,000,000, we know that y has to be greater than x by an even amount. And that even amount has to be a positive integer. This is only an integer when x is a perfect square. So x must be a perfect square. And not only that, this is the only value of k that works. If I fix x, there's only one value of k that will work here, that's good for us. That's interesting. Okay, so what I want to do here to solve the question is I want to count how many perfect squares there are less than 1,000,000, such that the corresponding value of y, when we compute y using this value of k, is also less than 1,000,000. Okay, so we need x to be a perfect square. And x plus 2k, which is equal to x plus 4 plus 4 root x. This also has to be less than 10 to the 6. So we're counting all values of x which satisfy this. Let's just check that, if I let x equal to 1, that the corresponding value of y does work. Let's just check. We can check a couple values here, actually. So if x equals 1, k is equal to 4, y is then equal to y is equal to 9. Then the arithmetic mean is 5. And the geometric mean is 3. Okay, so that works. I'm going to check one more value here. So x is equal to 4. This gives k is equal to 6. And y is equal to 4 plus 12 is equal to 16. Okay, so x plus y over 2 is equal to 10. And root xy, 16 times 4 is 64. Okay, so this is 8. Okay, and that also works. Cool. Okay, so it seems like we're correctly generating pairs of integers that satisfy satisfy the conditions we're given. Okay, so now, I think the best way to do this, the best way to figure out how many perfect squares satisfy this is to just look for well, why don't I treat this as a quadratic equation in root x. Solve for root x, and then we'll have to take the sort of first perfect square below whatever we get. So what do we have here? X plus 4 root x plus 4. Let's say it's equal to 10 to the 6. So let's let u equal to root x. So we have u squared plus 4u plus 4 minus 10 to the 6 is equal to 0. Hold on, I'm not sure if this... Right, this is giving us... Right, this is y for any value of x. We need y less than 1,000,000. And this is saying y will be less than 1,000,000 if root x. In fact, we got equality here, right? So y is this will result in y being equal to 1,000,000. Okay, so x is allowed to be any number from 1 up to 997. 998 will give us a value of y equal to 1,000,000, but we're told that y is strictly less than 1,000,000. So x can be from 1 to 997. Oh, does x have to be a perfect... X is any of the squares. Yeah. So the root of x, square root of x, can be from 1 to 997. So we're looking for all the perfect squares. I mean, the answer is 997, right? There are 997 perfect squares that have x ending up less than that. Okay. So we need x, root x, to be in 1, 2, all the way up to 997. So the answer, I believe, is 997. That was a cool problem. It did not turn out to be geometric the way I thought. My intuition was telling me that, I mean, when I wrote down the relation that we're looking for between the arithmetic and geometric mean, this one here, and then simplified it, this does give some kind of curve in the plane. Although it's not completely clear to me exactly what kind of curve it'll be. It could be an ellipse. Well, hold on. I don't know. Doesn't really matter. But this, I think, you know, writing this relation out in the first place and then simplifying it to this was a big thing. I played around a little bit with small values of x and y and figured out pretty quickly that we needed x and y to differ by an even amount. That was pretty key because then subbing that into here allowed me to write, allowed me to treat k as like a single parameter rather than dealing with two parameters. It was nice that things simplified to this, and this is what made me realize we needed x to be a perfect square. Yeah, so I'm fairly confident in this answer, but if I catch any mistakes or if I have any additional comments, I'll put them in the description. Thanks for watching.